So in this video, we are going to cover the last section of Unit 3, Section 4.9, which covers antiderivatives. Antiderivatives are exactly what they sound like, the antiderivative. Okay? So there are a lot of rules, like many things in calculus. But what we are going to do now is we are going to undo what we've been doing. You ready? Let's go. So you will notice, as you get going in this section, differentiation is a lot more straightforward than integration. And partially because differentiation, we're moving forward. We have a set number of rules, and we just need to follow them. Most complicated thing is when we get like a really crazy chain rule or product rule or quotient rule. But integration, there are all sorts of things that we end up doing, and it actually can become slightly overwhelming. The nice part about integration, or as we're calling it in this section, antiderivatives, sorry, my dog decides to bark now, is that we're only going to do the introduction to this, and we have more to learn in the next chapter, okay? All right. Antiderivatives. Our goal in this section is to study a process called integration, which reverses differentiation in the same way that division reverses multiplication. Thus, given a function of f, we'll be asked to find another function f whose derivative is f. Isn't that helpful? Notice the lowercase and uppercase f here. In other words, if I take the derivative, am I going to get my other function? So a function, capital F, is called an antiderivative of lowercase f on interval I, if f prime of x is equal to f of x for all x in that interval I. Okay, so let's look at an example. Suppose we have the function f of x equals x squared. And we wish to find a function, capital F of x, so that if I take the derivative of that, I get my initial function. So let's think about this. Let's think about the power rule, okay? So remember the power rule. If I'm getting something that's going to give me the derivative of x squared, okay, I start off with a power of what? Remember, when I take the derivative, the power goes down, right? So the antiderivative of this is going to go up. Now next, remember, I multiply by the power in front, but there is no number there, so I must be dividing by that power in front. However, that's not the only possibility. We could also possibly have the function of 1/3 x cubed plus 100. If we take the derivative of that, that will give us x squared. We could also have the function of 1/3 x cubed minus 4. And when we take the derivative of that, we still end up with just plain Jane x squared. So there are a lot of options here for the antiderivative that gives us x squared. So since these options really only differ by a constant, therefore, if capital F of x is an antiderivative of f of x, then so is f, capital F of x, plus c, the antiderivative of f for any constant c. So if f is an antiderivative on interval I, then the most general antiderivative of f on I is f of x plus c, where c is an arbitrary constant. Okay, always, 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 always remember the plus c at the end. So let's take a look at this. We're going to find the most general antiderivative of each of the following functions. So what we're starting off with is we've got f of x is sine of x. So remember, what we're doing is we're undoing this. We are thinking the derivative of what gives me the sine of x? Well, what about the derivative of cosine of x? Well, the derivative of cosine of x gives me negative sine of x, so that's a nope. Okay. So, well, that means that we need to have a negative sign get rid of, because a negative sign will give me a positive sign. So what about the derivative of the negative cosine of x? Well, yeah, if we take the derivative of that, that does give us the sine of x. So that works. So therefore, capital F of x is going to be the negative cosine of x. But don't forget, there's some constant c we can also take a derivative of that will cancel. Right, again, remember we're going backwards. So what we're doing here is if we take the derivative of this, if you take the derivative of your answer, you should get what you started with. Okay, so we're undoing the derivative, called the integral, called the antiderivative. Let's look at the next one. So here I've got f of x equals x to the negative 3. So let me change colors very quickly. There's a couple things I want you to think about. So again, you're saying the derivative of what with respect to x gives me x to the negative 3. Well, what's the opposite of the power rule? Because this is clearly power rule. Okay, so what's the opposite of the power rule? Now, when I take the derivative of the power rule, think about this. When I take the derivative of the power rule, right, the power goes down in front, and then I reduce the power by 1. So instead of multiplying by the power, I'm going to divide by the power. That's the opposite of multiply, right? But what power is it? Keep in mind that the power rule takes away 1. So the opposite of the power rule will be to add 1. And then instead of multiplying by that power, we're going to divide by that power. So this, if I take the derivative of this, whoops, erase that mark. If I take the derivative of this will give me x to the n. Alrighty then, so if I'm going to find my f of x, here I've got my x to the negative 3. I'm going to add 1 to that power, and then I'm going to divide by that power. And then, of course, don't forget I'm going to put a plus c. So this antiderivative is going to give me x to the negative 2 divided by negative 2. I'm just going to put the negative there, plus c. Oh, good job. Let's think about our basic antiderivative formulas. If f of x is an antiderivative of f of x, then the most general antiderivative of k times f of x is k times the antiderivative. If the f of x is the antiderivative of f and g of x is the antiderivative of g, then the most general antiderivative of f plus g of x is going to be f plus g of x. So in other words, I can add these antiderivatives together. Here's that power rule we were talking about before. If I'm taking the antiderivative of x to the n, then I'm going to add 1 to it, and then divide it by that power, and then add c. Next, if I start off with secant squared, I need to think to myself, what do I take the derivative of that gives me the secant squared? Oh, the tangent gives me the secant squared. Don't forget that plus c. Well, what about this? What derivative gives me this rule? Oh, No, the inverse sign. Exactly. Don't forget plus c. And of course, there are so many more. Think about all the derivative rules that we have learned in the last few chapters. That's why it's so important to remember them, because now we're going to do the opposite of them. All right. It does help to have a formula shirt, why can't I say it? A formula shirt. I actually would love a formula shirt. It would be helpful, sorry, let's get back to it. It would be helpful for you to have a formula sheet of your derivatives and antiderivatives nearby so that you can just keep in mind what you're working with. Let's go ahead and do an example. All right, so we want to find the most general antiderivative of this function, but I'm going to tell you right now, it's not going to be easy unless we rewrite everything. So I'm going to write this as 3x to the 1/2 minus 2 times x to the 1/3. Now I'm going to take the antiderivative. So I'm going to undo the derivative. So the 3 for this one goes along for the ride. And then for my x, I'm going to do 1/2 plus 1. And I'm going to divide that by 1/2 plus 1. Now keep in mind when I add 1, it's just really easy to think of it as 2 over 2 since it starts off as a 1/2. And that way the arithmetic isn't so interesting. Next term, -2 is going to go along for the ride. And then I have x to the 1/3. And I'm going to add 1 to it. But remember 1, if I'm dealing with 1/3, is going to be 3 over 3. And then I am dividing this by 1/3 plus 3 over 3. So let's simplify here. Oops, did you see what I forgot already? Yeah, don't forget that plus c. As a math student, you'll get good at writing the elongated plus c that you can squeeze in at the end. Alrighty, but we are not done yet. Keep in mind, this is not fully simplified. If I am dividing by a fraction, I'm actually multiplying by the reciprocal. So I'm going to multiply this first one by 2/3. Then I'm going to multiply the next one by 3/4. I'm getting rid of the fraction in the denominator. And then I'm just going to simplify. So here my 3's happen to cancel. I'm left with 2 x to the 3/2. Here my 2 will cancel with a 2 in the 4. And that's going to give me minus 3/2. And then plus c. That's my final answer. Remember, if I want to check antiderivatives, take your answer, your answer, which is f of x, and take the derivative of it. Do you get your original problem? If so, you did it right. For this next one, we're going to look at what's called a particular solution, not a general solution. A particular solution is basically a solution that finds c. Okay, so we don't just use any constant c. We want to find a specific value. And I do have a typo in your notes. Honestly, because I think the original one is a little confusing. So we're going to use some different numbers. All right. So first thing, we're going to start with f prime of x and take the antiderivative to find f of x. Okay, so we're going to take the antiderivative of this bad boy. So I've got 1, and then I've got x to the 0. So I'm going to add a power of 1 to that, and then divide by that power. Next, this one right here, it's easier if we think about it as x to the negative 2. So if I have x to the negative 2, I'm going to add 1 to that, and then I'm going to divide by that negative 2 plus 1, which is negative 1. Next, I'm going to put in here plus c, and then I'm going to simplify. So here I've got x to the 1 over 1 plus x to the negative 1, and that's not a plus because it was divided by a negative 1, plus c. Okay, now let's do some plugging and chugging. So now we're going to look at some plug and chug. So for our function, we're going to put in 1/2 for all of our x's. And then our output is going to be equal to 2. So my output is going to be 2 equals, and then I've got 1/2 minus 1/2 to the negative 1 plus c. And then what I need to do is solve that for c. So let's go ahead and do that. Here I've got 1/2 minus 2. And that's going to give me 2 equals 1/2 minus 2, negative 3/2 plus c. And then I'm going to add 3/2 to both sides. And I end up with 4, 6, 7 halves. So c is my 7 halves. And that means I can now fully define my antiderivative. So I'm going to write this down. X minus, and I can write it as x to the negative 1 or 1 over x. It's up to you. And then plus 7 halves, because the 7 halves was positive. And that's my final answer. Let's do this again, but with a second derivative. So in other words, I need to take the antiderivative twice to find out what's going on. So first thing I'm going to do is I'm going to find the first antiderivative. So I'm going to go from f double prime to f prime. The antiderivative of 2, think of 2 as like being 2 times x is 0. Okay? And then the antiderivative of cosine is a positive sign. And I'm going to add c. Now this is my first c because it's my first antiderivative. And I'm just going to clean house. So 2x plus sine of x plus c1. All right, next, I'm going to take the antiderivative again. So here, I'm going to have 2x to the 1. I'm going to add 1 to it and divide by that power. Next, I'm going to take the derivative of the sine of x. The antiderivative of the sine of x, and that's going to give me negative cosine of x. And then if I'm taking the antiderivative of c to the c sub 1, that's going to be c sub 1 times x, right? Because I went from x to the 0 to x to the 1, and then I'm going to have a second constant. So if I simplify that, I'm going to have 2x to the 2 divided by 2, which just gives me x to the 2. And then minus cosine of x plus c sub 1 times x plus c sub 2. Now here's my plug in chug stage. I actually have 2 plugs to chug. So I'm going to plug and chug, and I have 2 things to plug and chug. I'm going to start with the first one. F of 0 equals -1. So I've got my original function, f. The output is -1. The input is 0, so I'm ending up with 0 squared minus cosine of 0 plus c sub 1 times 0 plus c sub 2. Now notice what I end up with is -1 is equal to 0 minus 1 plus 0 plus c sub 2. So this is going to be -1 equals -1 plus c sub 2. If I add 1 to both sides, I see that c sub 2 is actually equal to 0. Neat. Well, that's okay. That's a constant, right? All right, let's do the second plug and chug. So f of pi over 2 is equal to 0. So let's plug and chug that thing. So the output is equal to 0. Pi over 2 is going to be squared, so I'm going to have pi squared over 4 minus cosine of pi over 2 plus pi over 2 times c sub 1. And then remember that we just found c sub 2 to be 0. So I do that, and simplify it. On the right side, I end up with this. And if I subtract that pi squared over 4 from both sides, I'm going to end up getting c sub 1 is going to give me negative pi over 2. So, doesn't that work? Now I have my answer. I'll put it all together. So therefore, f of x is going to be equal to x squared minus cosine of x minus pi over 2 times x. We don't have to write that plus 0 because we don't need it. All right. Neato, hey? So, what's a calculus section without a little bit of applications? So let's look at some story problems. We've got a particle is moving in a straight line and has an acceleration that's given by a of t equals 6t plus 4. Its initial velocity is v of 0 equals -6 centimeters per second. And its initial displacement is s of 0 equals 9. So they want us to find its general position at s of t. Although we do have some information that we can find its specific position function, but we're just finding the position function. So recall a couple of things, okay? That in this case, s is some position function, okay? So remember that velocity is the derivative of the position function, and that acceleration is the derivative of the velocity function. So if I want to find velocity, I need to start with my acceleration function that they gave me. So v of t is where I'm just going to take the antiderivative of this. So I'm going to have 6t. Now this t is a power of 1, so 1 plus 1 is 2. Divide by that power of 2. Plus 4. There's no t here. This is kind of like saying t to the 0. So this becomes 4t to the 1 divided by 1. And then don't forget your plus c. Okay, don't forget that. It's a big deal. All your problems are wrong without it. Next. They've given us this information here so I can do some plugging and chugging. So v of 0 is negative 6. So let me actually do a couple things first. Wait, sorry, I'm lying. Let me just clean house. Simplify this bad boy. Okay, so v of 0 is negative 6. And then I'm going to have 3 times 0 squared plus 4 times 0 plus c. So notice, it basically says that c is negative 6. Awesome. All right, so this means that my velocity function is 3t squared plus 4t, and then plus a minus 6 or just a minus 6. So that's my velocity function, and I am almost to the final thing, but I got to do one more antiderivative. So remember that the derivative of the position function is equal to the velocity function. So I need to take the antiderivative to find the position function. So I'm going to take the antiderivative. I'm going to have 3t to the 2 plus 1. So this is going to give me 3t to the 3 over 3. And then here it's t to the 1. So I'm going to have 4t squared divided by 2. Here I've got a minus 6. That's like saying t to the 0. So minus 6 t to the 1. And then plus c. And then I'm going to clean house and plug and chug. These 3's cancel. The 3's there cancel. 4 and 2 cancel as well. And now I've got that. So S of 0 is equal to 9 centimeters. So if I plug in 9 here and 0 in for my t's, it's always nice when they give us an input value of 0, because then it's easy to identify what your c is. And then this will give us our last piece needed for the final answer. S of t equals t cubed plus 2t squared minus 6t plus 9. Yeah, a lot of this is just going to be the power rule, okay? But you'll need the other ones too. Let's take a look at another example. A ball is thrown upward with an initial speed of 48 feet per second from the edge of a cliff that is 432 feet above the ground. So we want to find the height above the ground t seconds later. And then we want to look at what the maximum height is. So keep in mind, since we're on the planet Earth, we are basically dealing with the same gravitational force everywhere, which is going to give us 32 feet per second squared, or 9.8 meter per second squared. And since this problem is in feet, we're going to use the 32. So for A, if we want to find the height is the position function. But notice that we are given acceleration information. So the acceleration, which is, I should write, the derivative of the velocity function, is a negative 32. Because it's pulling you towards the Earth, right? Earth isn't trying to shove us off into space. It tries to keep us in. Although maybe if the Earth could figure that one out, we'd have less problems on this planet. Yeah, it's still nice being here, I guess. Okay, anyways, got distracted. A little dark there. Sorry about that. This COVID stuff's rough. Okay, so my velocity, the derivative of my velocity is a negative 32. So that means if I take the antiderivative, I'm going to end up with negative 32 times t plus c. Now, notice that it told me that it had an initial speed of 48 feet per second. So I can use that for my c. And it's thrown upward. So upward means away. Oops, up at the top of that screen there. You can't see what I'm writing. So if I'm throwing upward from the planet, that is away from the source of origin, so it's going to be a positive 48. My velocity function is going to be negative 32t plus 48. But we don't want my velocity function. We are looking for the height function, which is the position function. So the position function is, the derivative of that is equal to the velocity function. So if I want to find my position function, I need to take the antiderivative of the velocity. So t has a power of 1. I'm going to up that up by 1, so I'm going to get t squared, and I divide by the power. This is just a constant, 48, so it's like saying 48t to the 0. So I'm going to do 48t to the 1, and then divide by 1. I don't have to write that in there. And then I've got that plus c. Now, I'm going to do a couple of things just really quick. I just see this negative 32 divided by 2. I'm just going to simplify, run a little bit out of space. So I'm just going to simplify like that. I'm going to move this plus sign. Okay. Now, it did say it was thrown from the edge of a cliff, which is 432 feet above the ground, and that is my initial height. And it's off the ground, not under the ground, right? It's off the ground, so it's a positive c. So my position function here is going to be negative 16t squared plus 48t plus 432 feet. So that's my height at any time t. Next, when does it reach its maximum height? Well, the maximum height happens when you've got the velocity function equal to 0. So if I go back to my original velocity function, that's this bad boy right here, velocity. I'm going to say, okay, velocity equals 0 when I'm reaching the max height. So I'm going to say negative 32t plus 48 equals 0. I'm going to subtract 48 from both sides. And I'm going to divide by 32, by negative 32, and I'm going to get 1.5 seconds. Now, I would look at a picture of the velocity function to verify that before it's increasing and afterwards it's decreasing, or do a little sign test, okay, on that velocity function. All right, and that's when it reaches the maximum height, 1.5 seconds. Okay, that's the end. Whoops. That's the end of section 4.9. Keep in mind, it is really important to know some of your derivatives so that you can do antiderivatives. For example, if I have f of x equals the secant of theta times the tangent of theta, what's capital F of x going to be? Well, what do I take the derivative of to get secant theta tangent theta? Yeah, the secant theta. And just don't forget that plus c. Okay. All right. What about this? What do I take the derivative of to get 1 over x? Oh, yeah. The natural log of x. And don't forget your plus c. All right. Keep those formula sheets close. They're super handy. Have fun working on your homework.